Alright, let's go. Number 10. The Cosmic Latte. In 2002, astronomers Carl Glazebrook and Ivan Baldry at Johns Hopkins University embarked on one of the stranger scientific missions in the history of astronomy. They wanted to know the average color of the universe. Not a metaphor, not a thought experiment, but an actual measurable answer derived from the combined light of every star and galaxy we can observe. The result was not what anyone expected. To calculate it, Glazebrook and Baldry averaged the light output from more than 200,000 galaxies, accounting for their distance, their age, and the specific wavelengths of light they emit. The working assumption among most astronomers was that the answer would land somewhere in the blue-white range, reflecting the intense energy of young, hot stars burning across billions of years of cosmic history. The universe, in their imagination, was a bright and blazing place. It wasn't. The true average color of the universe is a warm, creamy beige, almost indistinguishable from a milky coffee. After a public naming competition that itself became a minor news story, the color was officially christened Cosmic Latte. Scientists had added up the light of 2 trillion galaxies and gotten the color of a morning drink. What that color actually tells us is quietly remarkable. The universe is beige because it is aging. Its earliest epochs were dominated by furiously hot blue-white stars, burning through their fuel at extraordinary rates. As those stars died and star formation slowed across cosmic history, the overall light shifted toward the warm end of the spectrum. The universe, in a measurable and literal sense, has mellowed. The cosmos is 13.8 billion years old, contains more galaxies than there are grains of sand on every beach on Earth, spans distances the human mind cannot genuinely comprehend, and its average color is the shade of a lukewarm latte. What other mundane surprises might be hiding inside the numbers? Number 9. The Himiko Cloud. In 2009, astronomer Masami Achi and his team at the University of Tokyo were analyzing deep field observations from the Subaru telescope in Hawaii when they found something that had no business existing at the time it existed. The object sat 12.9 billion light years away, meaning the light reaching their instruments had been traveling since the universe was barely 800 million years old. A cosmic infant still in the process of figuring out what it was. What they found in that infant universe was something enormous. At that era of cosmic history, astronomers expected to find small, turbulent proto-galaxies, modest collections of young stars just beginning to coalesce from primordial gas. The universe at 800 million years old was thought to be too young, too chaotic, and too diffuse to have assembled anything of truly impressive scale. Structure in the standard model of cosmology takes time. Billions of years of gravitational accumulation are required to build something large. The Himiko Cloud is approximately 55,000 light years across, roughly half the diameter of the Milky Way, and contains a mass approximately 40 billion times that of the Sun. It is a glowing blob of hydrogen gas, classified as a Lyman alpha blob, and it is one of the largest single objects ever found from the universe's earliest era. Its size, at that point in cosmic time, is genuinely unexplained. Named after a legendary and semi-mythical queen from ancient Japanese history, Himiko has been studied intensively since its discovery. Follow-up observations using the Atacama Large Millimeter Array suggested it might contain multiple merging galaxies at its core, each embedded within the giant gas cloud. That would explain some of its mass, but not all of it, and not entirely its scale. Objects of this size should not have had time to form this early. The standard model of structure formation struggles to account for it. If something this massive assembled itself in the universe's first billion years, what else was building in that early darkness that we haven't found yet? Number 8. The Cold Spot. In 2004, astronomers processing data from NASA's WMAP satellite, the Wilkinson Microwave Anisotropy Probe, were mapping the cosmic microwave background, the faint afterglow of radiation left over from the Big Bang itself. This map was supposed to show the universe in its infancy, a near-uniform field of ancient light with only tiny predictable temperature variations. What the data showed in the direction of the constellation Eridanus was something that had no satisfying explanation then, and still doesn't now. The cosmic microwave background is among the most carefully studied phenomena in all of science. Its temperature variations are minuscule, measured in millionths of a degree, and they follow statistical patterns consistent with our models of how the early universe developed. Small fluctuations were expected. The map was expected to be, in essence, a confirmation of what physicists already believed. Cosmology rarely delivers genuine surprises at this scale. There was a circular region of sky approximately 1.8 billion light years across, running measurably colder than everything around it, roughly 70 microkelvin below the background temperature. That number sounds small, but at cosmic scales it represents an anomaly so statistically improbable that astronomers have spent 2 decades trying to explain it. The Planck satellite confirmed it in 2013, ruling out instrumental error. The cold spot is real. A team from the University of Hawaii identified a supervoid in that region in 2015, a genuine underdensity of galaxies that could account for some of the cooling effect. But most analyses conclude the supervoid alone is insufficient to explain a cold spot this pronounced. The deficit of matter explains part of the temperature drop. It does not explain all of it. Several physicists have proposed, with mathematical seriousness, that the cold spot could be a bruise, a scar left on the fabric of our universe from a collision with a neighboring bubble universe during the earliest moments of cosmic inflation. A supervoid at the edge of the observable universe is strange enough. The possibility that the cold spot marks the point where our universe brushed against another, leaving a permanent imprint on the oldest light in existence, is something else entirely. Number 7. The cosmic raspberry. When astronomers studying the molecular cloud designated Sagittarius B2, a vast region of gas and dust near the center of our galaxy, approximately 26,000 light-years from Earth, began cataloging its chemical contents using radio telescope spectroscopy, they expected to find simple molecules. What they found instead was an organic chemistry laboratory operating at a scale that strains the imagination, producing compounds that have no obvious right to exist in the void between stars. Molecular clouds are among the coldest environments in the universe, hovering near absolute zero. They are also paradoxically some of the most chemically complex. Ultraviolet radiation from nearby stars drives chemical reactions in the gas, building increasingly complex molecules from simple atomic ingredients. Astronomers had detected alcohol molecules in space before. What Sagittarius B2 revealed was different in scale, different in a way that changes how you think about the chemistry of the cosmos. The cloud contains ethanol. It contains methanol. It contains vinyl alcohol and glycolaldehyde, a simple sugar. Most remarkably, it contains ethyl formate, the compound responsible for the smell of raspberries. Sagittarius B2 smells, in a technical and chemically accurate sense, of raspberries and rum. The cloud itself is estimated to contain quantities of alcohol so vast that expressing them in conventional units becomes almost meaningless. Billions upon billions of liters of organic compounds drifting through a region of space larger than our entire solar system many times over. The scientific significance beneath the absurdity is profound. The same molecular building blocks found in living organisms on Earth, sugars, alcohols, complex carbon chains, are being synthesized continuously at enormous scale throughout the interstellar medium. These compounds form in space, survive in space, and are delivered to young planetary systems when molecular clouds collapse to form new stars and their orbiting worlds. The ingredients for life are not rare. They are everywhere. The universe has been brewing organic chemistry for billions of years across distances we cannot meaningfully picture. If the raw materials for life assemble this readily and this abundantly in the space between stars, the question of whether life has arisen elsewhere stops being philosophical and starts being statistical. Number 6. The diamond planet. In 2012, a team of astronomers led by Niku Madhusudan at Yale University published an analysis of a planet called 55 Cancri E, now officially named Janssen, located 40 light-years from Earth in the constellation Cancer. The planet had been known for several years, detected by the transit method as it crossed in front of its host star. What Madhusudan's team proposed about its composition stopped astronomers mid-sentence. Most planets form from the same general mix of elements as their host stars. Earth's bulk composition, iron, oxygen, silicon, magnesium, reflects the chemistry of the cloud from which our solar system condensed. The same is broadly true across most planetary systems. Astronomers had cataloged hundreds of exoplanets by 2012, and while they varied in size and temperature, their underlying chemistry tended to follow recognizable patterns. 55 Cancri A did not. Madhusudan's analysis suggested that the planet's host star is rich in carbon relative to oxygen, a different chemical environment than our own sun, and that under the extreme pressures of a planet roughly twice Earth's diameter and 8 times its mass, the carbon would crystallize. The initial model proposed that approximately 1/3 of the planet's mass could be diamond. Not diamond-like, not diamond-adjacent, diamond. Crystallized carbon under planetary scale pressure, forming a layer potentially thousands of kilometers thick, beneath a surface where temperatures reach approximately 2,400 degrees Celsius. Subsequent observations, including data from the James Webb Space Telescope in 2023, have complicated the picture. JWST detected possible signs of a volatile atmosphere or surface lava ocean, suggesting the planet may be geologically more active and chemically more complex than the 2012 model indicated. The diamond interior model has not been ruled out. It has simply been joined by new layers of strangeness. Whether or not Janssen is precisely 1/3 diamond, it is unambiguously unlike anything in our solar system. 40 light-years away, a world smaller than Neptune sits roasting at temperatures that melt rock, possibly encasing a shell of crystallized carbon the size of a small planet. The rarest gemstone in human experience is, on cosmic scales, just another outcome of the right star and the right pressure. Number 5. The Great Nothing. In 1981, astronomer Robert Kirshner and his team at Harvard were conducting a survey of the large-scale distribution of galaxies, mapping in 3 dimensions how matter is arranged across hundreds of millions of light-years of space. The universe, theory predicted, should have a foamy structure. Galaxies clustered in filaments and walls, with voids between them that were large, yes, but not empty. Not truly empty. Even the void should contain scattered galaxies, thin threads of matter, the residue of cosmic structure. What Kirshner's team found in the direction of the constellation Bootes was a region that appeared to contain almost nothing at all. The Bootes void spans approximately 330 million light-years in diameter. To place that number in context, the distance from our Milky Way to the Andromeda Galaxy, our nearest large galactic neighbor, a journey so vast that light takes 2.5 million years to cross it, fits inside the Bootes void more than 100 times. It is not a gap in the cosmic web. It is an absence, on a scale that defies the models used to predict how structure forms in the universe. Where astronomers expected to find thousands of galaxies, they have detected approximately 60. The void is also anomalously nearly spherical, a shape that natural cosmic structures rarely achieve. Voids form through the complex interplay of gravity and the universe's expansion, and that process tends to produce irregular, asymmetric geometries. The near-perfect roundness of the Bootes void sits uneasily in the minds of cosmologists who try to account for it. Several explanations have been proposed. Perhaps the void formed through the merger of many smaller voids over billions of years, or through the amplification of an unusually underdense region seeded in the first moments after the Big Bang. These explanations are plausible. None of them is fully satisfying. Astronomer Greg Aldring has noted that if our galaxy sat at the center of the Bootes void, humans would not have discovered the existence of other galaxies until the 1980s. The void is so large that our most powerful telescopes would find nothing in any direction. If you placed the Milky Way at the center of the Bootes void and looked out in every direction, you would see no stars, no galaxies, no light from any other source. Just your galaxy, alone in a sphere of perfect darkness, 330 million light-years wide, with nothing to suggest the rest of the universe exists at all. Number 4. The Clockwork Signal, from 3 billion light-years away. In 2020, astronomers analyzing data from CHIME, the Canadian Hydrogen Intensity Mapping Experiment, a radio telescope in British Columbia, published a finding that introduced a new category of strangeness to an already deeply strange field of research. Among the hundreds of fast radio bursts cataloged in recent years, brief and blindingly powerful flashes of radio energy from deep space, one source had begun to reveal a pattern. Not a random pattern, a precise, repeating clockwork pattern that no known astrophysical process could cleanly explain. Fast radio bursts are already anomalous enough without adding periodicity to the mystery. They last milliseconds. They release energy equivalent to what the sun produces over the course of years or decades. They arrive from billions of light years away, from sources we can rarely identify and almost never study in detail. Most fire once and are never detected again. A smaller subset repeat, but irregularly, unpredictably, in ways consistent with random energetic processes. The source designated FRB 20121102A did something different. It pulsed on a cycle, active for approximately 90 days, silent for 67 days, then active again, the full period, roughly 157 days, repeating with a consistency precise enough to predict. Researchers led by Kaustubh Rajwad published the finding in the monthly notices of the Royal Astronomical Society. A second periodic FRB, designated FRB 180916.J0158+65, was identified by the CHIME collaboration in the same year, this one cycling every 16.35 days. Two separate sources, both following schedules, both 3 billion light-years away. The leading theories invoke orbital mechanics, perhaps a compact object like a neutron star orbiting a companion, with the radio bursts only beaming toward Earth for part of each cycle. Precessing jets, binary systems, and geometric viewing angles have all been proposed. None of these models fits both periodic FRBs without significant complications. The 157-day period in particular remains poorly explained by any single mechanism. Something 3 billion light-years away has been switching on and off like a lighthouse, on a schedule precise enough to mark a calendar by. We built the calendar. We have no idea what built the the schedule. Number 3. The star that is older than everything. In 2013, Howard Bond of the Space Telescope Science Institute published a paper in the Astrophysical Journal that created an immediate and uncomfortable problem. Bond and his team had used the Hubble Space Telescope to make refined measurements of a star called HD 140283, a dim, metal-poor subgiant visible with basic equipment in the constellation Libra, sitting just 190 light-years from Earth. Their best estimate of the star's age was 16.3 billion years. The universe